Sure, thanks. I don't have any slides, so I'm just going to quickly just give a high-level intro what this CTH genotyping initiative is about. So this, as Anna mentioned in the email invite, this is really a project aimed at addressing one of the 6 funders' requests for crops that end hunger. It's a multi-funder initiative, which predates one CGIAR to really help support the overall breeding modernization, CGNRs as a network. Sometime during the period of 2021 to 2023, through this CTH investments, we have seen a really significant jump in terms of genotyping usage to support routine breeding. And as of today, I think last I checked on our website, we now have actually more than 20 plus crops and animal species that have contributed markers, and they're routinely accessing the genotyping platforms on our shared services. And that covers all the low and mid density. There are also even crops that are not on the list yet, but they're accessible. Those are through the publicity and through the word of mouth from all the users, from the CGNRs. We have a lot of like non-CG crops as well that are not public, but are available or accessible through other portals as well. But they're all housed under the same genotyping platform. So for this $1 million investment from CTH, the priority is really to support NARS partners and a lot of first-time users to access genotyping solutions that are under our shared services. A lot of this are targeting one-off investments. During the duration, we had enabled actually a lot of small breeding programs to take the challenge of limited breeding resources to access genotyping tools out of the equation, and to really bring everybody together to start evaluating and start trying out how these genotyping solutions can be used and to demonstrate value in improving their breeding processes and efficiencies. We have also invested in a number of proof of concept for various genotyping applications, such as routine QA/QC, centralized trait deployment pipelines at select center partners, some DNA fingerprinting to look into relatedness of breeding materials. So a lot of this were done and supported through this $1 million CTH genotyping funds. We also did quite a number of low-density KASP marker validation, in some cases a revalidation of trait markers, and also onboarded a good number of mid-density genotyping panels. And all these are publicly accessible and with a fixed price, and I would say it's quite competitive and it's accessible and affordable by the standards of many breeding programs. So some high-level outcomes for the past 2 years that I think is worth highlighting and pointing out to the group here is that it's sort of like a venue that through this funding, it has enabled a lot of cross-learning from various molecular applications between CG and NARS partners. Like, for example, the RTB committees are coming together to share informatics know-how and tricks on designing and implementing marker platforms in their breeding programs. That there is some cross learnings between CG and NARS to how to integrate and routinely use QA/QC markers, using some of these markers for selections, for marker selection and also genomic selection. I must say that I think the CTH investment for the past 2 years has been a really good catalyst for sharing these molecular outputs from some of the larger crop programs, and it has sort of like scaled that into many of the smaller programs, and it also enabled a lot of the molecular markers that were previously just developed for a really specific use, and as we scale to more and more users and countries and genomic background, people realize that we need to continuously update and improve on these markers. So now I think I'm very, very proud to say that a lot of these markers, with the help and contribution from a lot of partners, they have now, a lot of them have sort of graduated from like being just off publication or, from an R&D setting, development into a really what we call a production ready markers for routine and very robust usage with wide applications. The other thing worth pointing out that is that really this investment has really enabled a lot of small breeding programs, the NARS programs, to be able to access molecular advances with the same platform that were only previously, and the pricing that were previously enjoyed by the larger users of these technology. So really the adoption curve for adopting genotyping, since it's a shared service, has really leveled the playing field for a lot of the smaller players. Now, finally, I just want to comment that this genotyping space is constantly evolving with new technologies coming up. And now the breeding resources lab service team, we're continuously on the lookout, engaging the end users, the breeding programs, understanding their needs, what are the new use cases in the horizon, also routinely engaging the vendors to see if there's more competitive pricing out there or new technologies out there, for our genotyping platforms, looking back for the past few years, if we were to benchmark that against global inflation rate of at least a minimum of 3-5% every year, I don't know the exact figure, but it's in that neighborhood. I think our genotyping cost has actually remained very, very competitive. And I think if you really compare that against the global inflation rate, I think our cost actually has come down. And this is all thanks to the support of all our CGIAR and NARS partners for the continuous usage and contributing to a marker inventory that we have that everybody can access. So with that, I will not take up more time. I'll hand it over to the next speaker. Thanks, Anna.
Thank you. Dr. Hugo, please.
Okay, thanks a lot. Can you hear me okay?
Yes.
Good morning, good evening, good day. Can you hear me and see me?
Yes, yes.
Oh, okay, thanks. So I really appreciate the opportunity just to briefly introduce the work that Mokhtar and Guillermo will be sharing with all of us. And for several reasons. I mean, for starters, this has been a really exciting pilot project done in RTV crops using potato with potato, so that polyploid species as a working model to really understand what's needed, not only in those crops, but also in other polyploid crops, such as those in the RTV world or beyond. But in addition, I think that this presentation it will share a lot of insight with all of us, because it's not only about success. I think that in many cases at the CGIAR we talk a lot about innovation, but we don't talk about failure. And a failure is in the path for success in innovation. Now, I'm not talking here about being making mistakes on purpose, but rather clever failure. Clever failure is about failing very quickly, very cheaply, and as early as possible in the process. And finally, the third message that I'd like to share with all of us is that, I mean, even though the word that Mokhtar and Guy will be sharing with all of us is about the use of a market for QC, I really think that we need to use this example from a wider perspective, because in many cases, I don't think that there is much point in moving, for instance, into genomic prediction unless you first optimize many stages of your breeding program. And for instance, unless you can really have a good enough level of certainty in terms of a genotype A in the field, it's actually A and not B, the gain that you will get from genomic prediction and from other more sophisticated approaches, it will by design be very limited. And actually, most breeding programs, they undervalue the huge impact of misclassified genotypes in your rate of genetic gain. So even though this might be just a narrow example, but again, unless any breeding program, not just a potato, a sweet potato, or an RTV breeding program, is able just to keep the level of misclassification at a very, very slow level, and that's doable in an affordable way with genetic markers, I think that should be one of the most basic requirements to progress to being ready for genomic selection, and also just to really achieve a good enough rate of genetic gain. So that's why I believe that this is an excellent example about the fact that usually not paid enough attention to in most reading programs, like simply the fact that making sure that genotype A is actually A and not B. And with that, I will leave it with Mokhtar and Guy to enlighten about us. Thanks so much again for the opportunity. Over to you.
Thank you, Dr. Hugo. Thank you very much. Mokhtar, you are co-host and you are able to share your presentation, please.
Yes, thank you, Anna. I'm sharing. Can you see my screen?
Yes, just put it in the presentation mode, please.
Yes. Let me see if I can remove this. I know it's hard. Yeah, it's okay. Now you can see it on full screen.
Yes, yes, thank you.
Okay, perfect. I have to move this. There is something here. Yeah. So thank you, Anna, and I will today present with Guy a presentation we had put together to show a little bit our experience into designing the KASP markers, validating them, and also the experience we have gained after using them for basically 2 years for potato, and also for quite some time doing some adjustment for sweet potato. And yeah, so just a little background why we need QC or why QC markers are essential for potato and sweet potato. I would say basically for any crop actually. It's for example, potato and sweet potato are vegetatively propagated, which means that after we create variability in the beginning of our cycles in the crossing blocks, actually those are the same individuals that we have to use throughout the whole cycle. So we have to make sure that once we take, as Hugo was saying right now, once we take the material on the field and make a selection for the next stage, we should make sure that actually we are using the same genotype back in the field. And even maybe more important is in the crossing block, if we make a parental selection, and it is very important to make sure that we are using the correct genotype, since parents are duplicated, let's say, in the crossing block. So we have to make sure that those duplicates are true duplicates. And since Hugo also was saying, we are jumping into like fully marker-assisted selection processes, and those mislabeling actually can cause a low accuracy of to selection, and that consequently would lead to a low genetic gain. Then we saw KASP markers as an option because they have a high discriminatory ability, which is very important for QC analysis, and the design is quite easy. And as Eng also said, it's quite affordable cost and very good also turnaround time, which would mean like maybe at most 3 weeks after we, let's say, send the results. It would be like the longest waiting time, I would say. And then we have been using CASP markers in the breeding program and also in the pre-breeding program. So we actually had quite some experience in using CASP markers. So using them routinely would not be a big issue. And then we could, with CASP markers, have a simple analytic workflow, which would allow, in a practical, let's say, point of view, fast decisions, which means that in the crossing block, for example, before starting the crosses, actually, we should make sure that the individuals in the crossing block are correctly labeled before making the crosses. So we would not need to make crosses and then discard them. So for all those reasons, we designed a marker panel for potato. I will start the presentation with potato part, and then Guy will follow up with the sweet potato part. So actually, we use cell cap markers from the Infinium array on 2 breeding populations, like the lowland, tropics, and virus-resistant population, and also the late blight heat-tolerant population. So after filtering for basically minor allele frequency and linkage disequilibrium, we had selected several markers for design that we then validated, comparing somehow the results we had from the CASP calls and what we had from the Infinium array. And also after validating some of the markers based on their performance and quality, we ended up with 21 markers that we decided to use in our routine breeding work. And those 21 markers, actually, we were aiming to have 24, meaning 2 markers per chromosome, but yeah, 3 of them did not work. And then you can see in the right, like the 21 markers can actually, or could actually on our validation panel separate clearly all the genotypes, including half SIGs and full SIGs with the tetraploid dosage. So given that, we had done some routine work with those CASP markers, and actually we used those 21 CASP markers for QC that we had designed for QC, and then we added 2 more markers, which are trait markers actually. One is for late blight resistance, and one also is for PVY resistance. I mean, it's just like, okay, let's just add the markers. It adds some variability. We can get the information for resistance to diseases, but also those markers could actually be added up to the existing QC markers to add more variability. So we had genotyped over 5,000 samples for potato, with basically quite some good rate of missing data, I would say, for the genotype, apart from one batch that we sent that had relatively higher missing data rate. And also the marker rate also, yeah, it is very variable. We could see from one submission, we had very little missing data, or maybe none from a marker, to 14, 15% with different another submission. And what we did also was to genotype our material from the LTVR from our crossing block. So which means, let me see if I can get my pointer. Yes, I can. So here we have genotype material from our crossing block from the 2 breeding pipelines. And yeah, we could actually, after running the QC analysis, identify 50 and 130 individuals from our 2 breeding pipelines that were mislabeled, and actually we could remove all those process because the process took some time. So we actually did the process before we got the results. So we removed anyway those seeds that are originating from these identified individuals as mislabeled. And also for the last submissions, what we did was include also the same control genotype in every plate that we send basically. So we have used the same control genotype for 26 plates for the last submission. And later we will discuss the different goals that we had from that same genotype. So CASP markers for tetraploid, some of them that we validated were very good. You can see here the separation of the different dosage groups. So for potatoes, so here we don't have the other, let's say, group, but here, for example, we have all dosage levels, even for this is for the diploid goals. And then when we run the tetraploid clones, we could, and that is what we would expect, that the diploid calling would be respected, and we can see it here. And for like, this is another marker, but just zooming in only, so you can see that even for diploid, we can see that this marker actually can give us the right dosage that we would expect for all the genotypes. Then we had also some complicated markers, which, for example, here, doing the tetraploid dosage for this marker, we can see that we have a lot of missing data because the algorithm could not really assign the correct dosage to all these individuals. So we have to somehow trick, I mean, it's not a trick the program, but to force it to tell, okay, we want 5 classes. So then we can somehow have the 5 classes if they exist in the material, but this is still not yielding enough data. Like we have some places where the marker could not be called anyway, could not be called. And but yeah, here also we had the same issue, but what I want to say here is that it is possible to correct for these little issues, but it has to be done actually marker by marker. So here, after forcing, like as you can see here with the diploid goals, it is not like the first marker that we saw before with the 5 different classes well shown. But here it kind of separates it into 4 different classes here. Then we have to force the program and tell, hey, look, we have 5 classes. So it kind of tries to find the different 5 classes, which is fine, but it takes some time, and then it can be very arbitrary in some cases where the classes are not really well, like the separation between the classes is not well defined. And as I was saying before, we had used also several, like the same tech for several plates. And for potato, what we saw is we had different groups of markers, I would say. For example, those that in diploid form actually are showing the same call from the results we get from the raw data. And after we do the tetraploid dosage, we can see that some of the individuals are assigned into a different group, which is per se not a big issue because we can actually correct for this as we saw earlier. But it would mean that we would have to do it by hand actually. And if we look at this other marker where we have this different genotype for the same, like this different call for the same genotype. And also, like as you can see, once we remove those, what we used to do is just if we have this kind of situation, we remove basically the marker information from that plate. So we can run the tetraploid so that only with the markers that allow us to, like, I mean, only with the markers that show the same codes for the same individual, which means that we are losing also information by trying to correct for these issues. So just as a short summary for potato, we have used it and we will keep using it until we have a better solution, because it works and it just is computationally a little heavy, and it takes time to process the data for tetraploid. But yeah, I have no doubt that CASP markers would keep being useful for potato until we find another way to do quality control analysis for tetraploid. So now I will give it to Guy. I don't know if you want me to run the slide or if you want to share your own screen.
I don't know, it doesn't matter, you can do it.
Okay.
Thanks. All right, so we decided to add a little bit more complication, right, when we try to do it sweet potato, which is hexaploid. So we had sequenced over 500 individuals from several breeding programs in Africa using DART-seq, and then select some of them to become our QC panel. So at first we had designed 30, which was this first test we ran. And because this was the first time we were ever doing any analysis with Intertech, we sent 4 plates, 2 of them silica gel dried and 2 of them freeze dried. And each one of them was applied a different buffer during DNA extraction. But that turns out to become an interesting exercise for us to compare, right? How reproducible the markers were. So at first, for the first 30 markers, we had only successfully amplified and found polymorphism for 12 SNPs. So we decided to increase that number of markers, adding more, like 30 more SNPs to the panel. And there was the second round of verification we ran, sending exactly the same samples, 94 samples, only 1 plate we sent at that time. And Intertech sent to us 2 results, each one with a different dilution of the DNA. And we also used that for comparing, right, how reproducible the markers were. So that turns out to be good. So we could understand more or less how we could work with CASP markers and sweet potato. If you go to the next slide, Mokhtar, we are going to see the results of the amplification, so the raw data, and the next one is going to show the dosage calling, right? So now we expect up to 7 different classes, right? 2 homozygous and 5 heterozygous classes. We were successful in calling the dosage for many of them. These are the ones that we ended up selecting. And then we decided to move on for the validation, for the application step, right? So if we go to the next slide, we are going to see that we have fingerprinted our 2 training populations, genomic selection training populations, one from CIP and the other from NACRI. They had different population sizes, so CIP took 13 plates and NACRI took 5 plates. And this is represented by the red dots, right? So these are the first fingerprints we did. And we used 30 of those CASPers that we found that worked fine for dosage calling. And then those 18 plates were collected from the screen house, right? Where we multiplied the clones. And then when we planted them on the field, we wanted to double check, right? To do the QC. And then we select randomly some of these individuals. So 3 plates came out of CIP field, and 1 plate came out of NACRI field, and that's represented by the blue dots, right? So this is one first thing we realized when I first saw the results. Maybe for diploids, it's easy to do it in separate rounds, but for hexaploids, it turns out to be a lot of trouble, right? Because they won't match and this is expected, of course, right? But it turns out it brought to us a lot of trouble when we were trying to, you know, count the matches and the mismatches along the population. So if we go to the next slide, we are going to see for some issues we had with a couple of SNPs, right? They appeared very differently in both runs. So we decided basically to exclude them. And everything we were hoping for was to find something like SNP 38, right? Even though they were in different moments, they still keep their organized dosage calls, right? And when we apply those things for analyzing the samples, as in the next slide, we see that, of course, it's easy for a SNP like 38, but not as easy for some other SNPs, right? Because they become just way too messy, even to analyze it within runs, right? This is a positive control we have for 18 plates in the first round when we fingerprinted the whole population. And then the same positive control used in the second round when we collect the samples out of the field, right? So of course it works beautifully for SNP 38, but not so beautiful for many of the SNPs we had. So we had to do basically this comparison by hand because we couldn't rely only on the dosage calling. Because again, even though the colors, right, the dosages were called separately for both runs, we would still have to compare them in the same plot and see if the individuals were matching. So we have an example in the next slide of one of those individuals, right? So in the case of SNP 38, we can see that they were called with the same dose, right, as one. But for some other SNPs, they sometimes are in the same color, sometimes they are not, which makes things very difficult because we cannot, again, rely only on the dosage calling. We'll still have to look plot by plot and compare whether the individual is the same or not. So we basically try to do it, and that's the results of the next slide. By basically counting the number of matches and mismatches, and this is the distribution for each one of the population. So the first one, UGP, stands for CIP, Uganda, and the second one, UGN, stands for NACRI. And as you can see, we can recognize those individuals that are not matches for sure, right? But still, all of them are going to show some level of mismatch, which makes things very hard for us to decide in, for example, where the threshold is, right? What's the number of markers that we are going to choose to define whether they are matches or mismatches. So it turns out that our experience with KASP is at least for quality control, right? Because we are using it for marker-assisted selection. It seems to be working well in terms of what we decide we want to see. But for quality control, as I said, we are having some trouble in dealing with these, these different runs, which is clear that it's going to happen in breeding operations, right? And the need of doing, all this dosage calling and even the counting of matches and mismatchings by hand. So if we move to the next slide, I think it's the last one I wanted to talk about, is we did a little bit of exercise doing simulations of a 8x8 allele, which is very similar to the samples of the first plates we sent for validation. So we did this analysis by simulating this huge allele with 30 individuals per family. So 64 full seed families, right, with 30 individuals each. And then we had the markers simulated, and then we want to see if we could find the parents. So if we, by doing so, we used a different number of markers. So we started with 10 just to have a low number to see what was going to happen, and then increased to 30, which was the number we were using, and then to 60 and 90, right? Just to compare what the evolution was going to be. And we also randomly placed some missing data. So the red ones represent 0 missing data, the green ones represent 10% of missing data, and 20, and the blue one represents 20% of missing data. So if we look for the crosses, for example, we can see that if we are doing it with the 30 and 10% of missing data, we are going to have more or less 75% of true assignments. But even though this is kind of a big number, this is not the problem. The problem is the level of confidence, which is the panel we have below. So the confidence we have is below 80% for the crosses, right? And the same thing happens when we do with the mom, like we know that the father and we want to know the mother, and the same thing with the dads, right? We know the dad and then we want to know the mom. The level of confidence when we are using 30 KASP markers with 10%, let's say, of missing data, which is pretty usual, is going to be below 80, which is not as high as one would expect, right? We can only achieve something close to 100% of true assignments with no missing data, or at most 10% of missing data, and still the let's say 95% of confidence would be found only for half of the samples analyzed. So of course that put us in a hard position in deciding whether we want to keep doing quality control for sweet potato, hexaploid sweet potato with 30 KASP markers, right? Because we know that the confidence is not going to be big, and even the level of true assignments is not as high as one would expect by using molecular markers, or at least more molecular markers, right? I think that leads us to the conclusions. Maybe Mokhtar, you want to go ahead?
Oh, okay. So as conclusions, we just saw that KASP markers actually work. They demonstrated a good, actually, discriminatory ability, making them suitable for identity analysis, but I would say not for high or high-ploidy levels. For low-ploidy or diploid material, it may be a very good option. But for, let's say, polyploid, it can be quite challenging to process the data, and that consequently would have issues on having the results on time to make decisions. And also, we have seen that the control genotype had different calls for the same marker across different plates, which also can be an issue for consistency if you want to do the analysis on a long term. And also, continuous efforts are required to identify and select markers that maintain that consistent performance over time. Or I would think that a strategic effort would basically be supporting on designing a dark side panel for QC analysis, where we could have basically about 100 to 150 markers. In that marker set, we could include also some trade markers. So when you do QC analysis, you can actually have the information if it is not available yet under your trade. But the idea is implementing or designing dart tag panel of 100 to 150 markers for quality control analysis and parental verification. So this is basically a summary of our experience with CASP markers for potato and sweet potato, and we would be happy to take any questions you may have.
Thank you very much, Mokhtar. Thank you very much, Guillermo. Wonderful presentation, and I think the results are really very, very good. Thank you for all the support. So we can go for questions. We already have here a couple of questions. Guillermo already answered to Jim. I'm not sure if Jim wants to expand or not, so you can unmute yourself and you can ask. Otherwise, Jim, if you are okay, we can go for the question of Ismail.
No, I think it's clear. Thank you.
Thank you. So Ismail, do you want to ask the question directly to Mokhtar, or do you want that I read it? You can unmute yourself, please.
Can you hear me?
Yes.
Yes. No, just first great presentation by Mokhtar and his colleague. I wanted to find out the genotyping of the crossing block and the statistic that was given. Was it genotyping of the individual plants representing each parent in the crossing block, or the progenies that came from those crosses, or is it both? In one slide to the statistics, yes.
Yes, here it is. These are the individual plants in the crossing block. For each pipeline, we actually had 40 parents, but you know, the female parents were, we had 5 plants of single female parents and 3 plants of single male parents. So it ended up having these numbers in the crossing block, and due to the fact that some plants may die or something may happen to them, or we remove these samples from the analysis, but these are the individual plants in the crossing block.
Okay, that clarifies.
Mm-hmm.
So we have also a question from Gary. Gary, do you want to ask directly the question, please?
Yeah, I was just wondering, you know, if we have to go to a higher density system for quality control, you know, how much does a relatively low density dart tag panel cost? We might be able to use the same system for genomic selection, for genome profiling. Is that a possibility?
Yeah, so that's exactly what we are thinking of doing with sweet potato, at least, because we have to have these individuals genotyped anyways for getting the genomic relationship matrices. And if you need to increase the number of CASP markers to 100 or 150, as Mokhtar put, that means it's going to be just as expensive as doing mid-density panels like dart tag, right? And on top of that, dart tag also provides the dosage calling already, which means that the breeders are going to be able to, you know, base their decisions without the need of support, you know, of bioinformaticians like us. So I would say that this is more or less the ideal platform, or something we want to test, and we are actually doing it right now for sweet potato. I'm not sure how Mokhtar is thinking about it in terms of potato, but yeah, that's an excellent idea for sure.
But yeah, sorry, just to follow up, it's pretty expensive still for very sort of high volume applications, isn't it? I mean, we're talking what, $10 to $15 a sample?
Right.
Yeah.
Yeah.
But
if we need to increase the number of CASP markers to 100, for example, that's going to cost more or less the same, if I'm not mistaken.
Yeah, for sure. So, but it seems worth doing for, I mean, the consequences of misidentifying a parent are huge.
Right.
So we need to do the quality control on every plant
Right.
in these crossing blocks, I think. And we just need to invest whatever it requires to make sure we're making the correct crosses. And I don't know if we have a standard operating procedure for crossing block quality control. The consequences, I think, are less important farther down the line, but yeah, we really need to be sure what we're putting in to those and what we're crossing, don't we?
Exactly. Yeah, I totally
Yeah.
agree. That's why I ran that simulation, because we wanted to check the crosses, right? And if we cannot do with 30 markers, we need to pursue other alternatives for sweet potato at least.
Yeah, and for potato, it is basically the same case. And the good thing if with dart tag markers would be that the dart tag markers would be selected from the already existing dart tag set, which means that in the early stages of the breeding program, of the breeding cycle, if we do the dart tag for the genomic relationship matrix, we would have actually those markers from the individuals of the breeding cycle. And then at the end or anytime in the breeding cycle, if we want to assess the identity, we don't need to actually run or re-genotype the supposed references. So we would just extract the marker information from the new samples and compare it to already existing data, which is also a good thing. And I think also given the marker density, and maybe will tell us, maybe it would not have to cost $11 per sample, but maybe the cost can be a little lower. Putting the fact that also the dart tag marker panel had been updated for potato, and we reduced somehow the number of markers.
And do you want to comment on that?
Yeah, thanks. Yeah, I think this is actually a sort of like a gap in the current shared service setup, but we're fully acknowledging that, once you go over 50 markers, actually KASP marker just for the value investment that we're putting in, it's actually have a what you get is really coming down the value, because they're basically the way it's priced is by assay, whereas the custom amplicon, the sequencing based approach, is actually starting to win out in terms of cost versus amount of information that you're going to get. Actually we are actually thinking to create negotiate a different pricing structure for sub 1,000 markers, like between like 50 to 300-400 markers for these type of applications. It will not be sort of like, right now we're paying like $12, for example, for up to 4,000 markers. It won't be exactly like, if it's 100, it won't be 10% that. That's not going to happen, because there's a lot of fixed costs that are involved in extraction and library prep and all that. But we do expect some amount of reduction to hopefully get to the price of $6-7 that will be there. That would then really give us an advantage of having a lot more markers for some of these applications. It may not be really required by some of the lower ploidy crops like rice or others, that they really have worked out, low number of markers can actually, give them the good results already and with good confidence. But for some of the higher ploidy, I think with the dosage calling ability for dart tag, that's certainly something that we are really looking into. Yes, I think Damaris has a hand.
Yes, Damaris, please.
Yeah, thank you. And I just want to say thank you so much to the two presenters, and just seeing the challenges they have, obviously because of the ploidy, which are some of the things we're dealing with also. I mean, we've had the same experiences with finger millet, but it's different because it's not an auto-tetraploid. I was just wondering, because I mean, now the discussion is shifting towards dart tag, which obviously is expensive. I mean, the KASP assay would still be really good, but I was just wondering, and I'm quite ignorant in this, wouldn't it be possible to find even just 10 genome-specific markers that you can use in KASP, because for quick hybridity confirmation, you just need a few. So you can still retain some 10 highly polymorphic but genome-specific that you're not worrying about the dosage. But then obviously invest a lot more on the DART tag for a larger panel. Obviously, it's cost effective if you have more markers in the DART tag panel. But I'm just wondering, is it like really not going to work at all with the KASP assays? Because I mean, if you can find just a few highly polymorphic, genome specific, that you don't have to worry about the dosage, which the KASP platform will not give you very well. And that you'll still have most breeders affording and utilizing on a daily basis. And I think now you have the genome, the reference genome for sweet potato. It should be possible to be able to identify even just 10 genome specific markers that you can use in the KASP platform.
Oh, yeah.
Guillermo, which of you want to respond?
Or yeah, no, just a quick thought. Thank you for the question. I think that would be ideal. The problem is sweet potato and potato are red hybrid crops, right? So we are dealing with this redundancy of SNPs for a long time, right? Because they are biallelic, and we have to distinguish among, 5 different classes of, in the case of sweet potato, of heterozygous, right? And I also find it difficult to find such a set of SNPs that would be useful for a broad diversity that all breeding programs would need, right? It seems to me that would be very specific to some breeding programs, and once they introduce some diversity, for example, that would need to be, reviewed and reevaluated. So I understand how it goes with, autogamous crops, right? But for hybrid crops like potato and sweet potato, I'm not sure if we can do it. Maybe I'm missing something.
I just wanted to add the fact that not just within the breeding program, like not just between breeding programs, but within the same breeding program, you can have actually different pipelines using different materials. So if we want a consensus panel that can be used by everyone, because sometimes we just put all samples in the same batches for submission just to reach those 4x4 number of plates. So I think that can be an option, but would be very hard to find markers that can be discriminant across population, and with this with the low number also of markers.
Thank you, Petra. You can unmute yourself, and after Jim.
Thank you, Anna. And thank you, Mokhtar and Guy, for a very nice presentation, and very nice to see these nice results. And also, Damaris, you had a very good point there with using the KASP for quality control. Yes, Gary, DART tag, extremely good to get such a panel. Yes, we are talking to DART to get a lower price, but Guy, as you know, DNA extraction high throughput for sweet potato is not the easiest. It's one of our most critical and most difficult crops to work with. So, and if you think of DART, then all the assays are done in one sample. So you have, if you now have 150,000, 4,000 markers, it's all from one sample, from that little bit of DNA. It's getting all the results. So it needs an extreme high quality DNA. And Gary, I'm afraid that costs some money too. So yes, we can lower the price, but still we cannot get so low as for KASP, where you only have one assay per sample, which allows a little bit more rougher DNA and in that way a cheaper price. That was what I wanted to add. Thanks.
Thank you, Petra.
Thank you, Petra.
Jim, do you want to ask your question?
No, in fact, I haven't kept up to date with platforms. I was just asking Eng if there are maybe other considerations to be made in the realm of highly multiplexed assays.
Yeah, Jim, so just quickly, I think we are continuously evaluating the platforms and any feedback from other users, what's out there in the horizon. Actually, even without going out there and really fishing for what's out there, a lot of vendors, since that, you know, we're getting some traction with the CG platforms, a lot of new vendors and service providers are also, you know, routinely reaching out to us. But I think we're still in a space where we're trying to balance out between having too many options and then with you know what's really the major use case and the usage here. Because if we start splitting, then you know it's not just really the genotyping cost per se, because there's other costs to consider as well, like logistics and the workflow and how that data gets handled by our breeding IT group eventually. So there's all these other hidden costs that we're also factoring in, and how much does it scale. So yeah, it's never as simple as, you know, jumping from like a $10 to $8, because we're always looking at from a multiple angle, what would be the ultimate implication for the CGIAR assessors. So, but and nonetheless, we're continuously evaluating.
Thanks. Yeah, I caught most of what you said, but at least for me, it was a little pixelated. But I did wonder, like Gary pointed out, you know, that there may be a broader need for a lower range of medium density genotyping in the, you know, few hundreds or lower range, that maybe there will be a broader need that you'd be looking for something at that lower level of mid density markers.
Okay, we are already on the time. I'm not sure if anybody want to ask something else. Otherwise, can follow up. We will share the PDF of this presentation, also the record. I'm really very thankful to all, particularly Dr. Hugo, Mokhtar, Guillermo, to all the funders, and also to the communication teams that helped to set up also these meetings. And hope you enjoyed. And any question, please just reach us. Thank you.
Thank you, Anna. Thank you, Guy.
Thank you. Bye.
Thank you.
Thanks, all. Nice presentations.
Thank you. Bye.